Hello, I'm Morgan Frank from the University of Pittsburgh, and I'm excited to tell you about this project looking at unemployment risk and AI exposure. So, a lot of studies are out there trying to figure out which occupations and which workers are most exposed to what technology can do, most exposed to automation from AI. And the fact that automation might be occurring out there has created a lot of concern in the public sphere for the potential of job loss. To highlight this, I've provided a few headlines from some notable news sources, including CNN Business, Business Insider, and Forbes magazine, all highlighting this concern that large language models might impact people's job security. However, the conclusions from these common business-oriented news sources is not always cohesive. For example, on the right, I'm highlighting a headline from The Atlantic and another one from Business Insider that are published just a couple weeks apart, with reaching completely opposite conclusions. The Atlantic headline reads, How ChatGPT Will Destabilize White-Collar Work, while Business Insider's headline reads, ChatGPT is the MySpace of AI. It's fun, but is far from taking your white-collar job. So this leads to a natural question. Who's right? Should we really be worried about the current wave of AI taking away people's jobs? Fortunately, there are several studies in the literature that try to estimate which jobs, which skills, which workers are most exposed to automation from AI. However, I think there's a bit of a disconnect between these studies and what they provide as sort of validation for their methods and actual data reflecting who's losing their jobs. To highlight this and why this might matter, of course, there are several studies looking at AI exposure, but let's focus on just two for now, and then we'll expand our scope to consider a few more. So to begin with, let's focus on the Fry-Osborne study out of Oxford University. This is a super well-known study. I'm sure many of you are familiar with it too. It's been available, at least from when it first appeared as a preprint in 2013. This paper has been available for over a decade and has been extremely well cited. Last I checked on Google Scholar, this study had over 14,000 citations, indicating that scores from this study are being used by researchers and by policymakers to try to predict which workers might be automated. Now, what they did in this study is they focused on just 9 different skills that they thought represented bottlenecks to automation from the AI of that time. And they used those bottlenecks compared to occupations that were certainly automatable and certainly not automatable to develop a model to figure out how likely occupations in between those two categories were to be automated. Combining those occupation scores with employment statistics in the US, they produced this histogram, you see this colorful histogram, and concluded alarmingly that 47% of US employment had high probability of computerization. Now, they're very clear that although there's a potential for automation from AI or computers to remove people's employment, that's not what they're showing you here. They say, in fact, we make no attempt to estimate the number of jobs that will actually be automated. So how should we think about this 47%? What does this fraction of exposure mean? To help you get a sense for what these scores actually correspond to in the labor market, they provide these two results. The first showing that occupations with high probability of computerization tend to be lower earning occupations. The second showing that high probability of computerization occupations tend to be less likely to require a bachelor's degree. So these are the results that you get. And I question if this is really a validation that relates these job level estimates or occupation level estimates with the potential for job loss. Further, this study was over a decade old. You might ask yourself, is this really the right set of estimates to be using for the AI we're talking about today? Generative AI systems like image generators and large language models. And the answer you might reach is maybe no. In fact, if you go back and look at their paper, they operate under the assumption that creativity actually can't be automated. And maybe that felt true a decade ago, but more recently, it kind of depends on how you define creativity, but it seems like large language models and generative image makers are perhaps performing some form of creative work. So this just goes to show you that maybe the estimates about AI and computerization of the past need to be updated regularly. Let's compare to a much more recent study. So here I'm talking about the GPTs are GPTs paper. that was focused specifically on large language models like ChatGPT. This paper was recently published in Science Magazine, but first appeared as a preprint in August 2023. It's a collaboration between the data science team at OpenAI and Daniel Rock at the Wharton School. Again, this paper, it's much newer, but again, it's still very well cited. Last I checked, it had over 500 citations on Google Scholar. The approach here is pretty different. Instead of focusing on just 9 skills, they're focusing on a set of thousands of detailed workplace activities and workplace tasks, and actually going out and asking both people online and asking ChatGPT itself which of those workplace activities the LLM might be able to perform. Again, they arrive at some set of scores for each task or each DWA, which you can then aggregate to an overall exposure score for each occupation in the US. Are these occupation exposure scores correlated with job disruption or other labor market factors that might be useful to predict? They provide these outcome in the main, or at least in the preprint. The first thing they find is pretty fun, which is that the human scores are actually well correlated with ChatGPT's self-assessment. So that's pretty interesting. The other thing they find is that the occupations with higher exposure to LLMs tend to be higher earning occupations, and also occupations with higher educational requirements. So more workers with bachelor's degrees are exposed according to the conclusion of this result. So this is really interesting because in just a decade's time, we've had 2 studies that are focused on an appreciably similar task, identifying which occupations have exposure to automate, or might be exposed, have some exposure to what AI can do, but they reach completely opposite conclusions. The Fry-Osborne study found that low-wage, low-educated occupations have more exposure, while the more recent paper focused on LLMs shows completely the opposite. Higher earning occupations requiring more education are actually more exposed to automation from large language models. So now if I'm tasked with actually figuring out which workers in the next few years might lose their jobs because of large language models, which set of estimates should I use? If one study predicts wages or education better than the other study, would that convince you to use their estimates to predict job disruption from AI? Both studies, I mean, I guess if you were forced to, you would probably pick the OpenAI study just because they were focused on LLMs, while the Fry-Osborne study, LLMs didn't exist a decade ago. But it just goes to show you that we should be focused on the empirics of job disruption if our goal is to talk about how AI might disrupt jobs. Now, this seems like a challenge because the typical data available from the government isn't really detailed enough to give us job separations or unemployment stratified by industry or stratified by occupation, and also stratified by region. So for example, states or counties. The best that I could find usually comes from the US Bureau of Labor Statistics. You can get some information on how technology might relate to changes of skill requirements within occupations by looking at something like the ONET database or maybe looking at job postings. If you wanted data on job separation rates, you could look at the Job Openings and Labor Turnover Survey, JOLTS, which gives you monthly total separation rates by state, but is not stratified by sector or by occupation. Sometimes job separations that result when workers don't adapt to changing skill demands. In rare cases, those workers won't find another job and will receive unemployment benefits as a result. And if you wanted to try to study that outcome, I think the best you might find is local area unemployment statistics, which again is aggregated at the monthly state level and is not typically stratified by sector or by occupation. So this makes it very challenging to actually study what I think is the true pipeline of job disruption and job loss from AI. New technology very frequently changes the skills that are demanded by an occupation, and sometimes workers adapt and don't lose their job. Sometimes they fail to adapt, and when that occurs, job separations can happen. Either the worker quits or is fired, and when those job separations occur, even more rarely, an outcome can be that those workers fail to find their next job and become unemployed. So I'd really like to have detailed data that's stratified by sector or occupation for each parts of that pipeline And so far, what I've been able to find is really interesting data that allows me to actually describe the probability of receiving unemployment by state by month and actually stratify that by occupation type. So here to do this, we're actually going to use data from the Education and Training Administration Agency within the US Department of Labor. They collect monthly statistics from each state's unemployment insurance program, detailing the most recent occupation of every unemployment recipient each month. We're going to use that information to calculate a probability of receiving unemployment given your occupation, state, and month, and I'm going to call this probability unemployment risk. Now, this is the same unemployment risk calculation from the last slide. What's nice about unemployment risk is it varies by time, it varies by region, and it varies by major occupations, so 2-digit SOC code. And if you apply Bayes' theorem to it, we can relate it to some more typical labor statistics that I think most of us would be more used to. So for example here, you can see that the unemployment risk is equal to the probability that an unemployment recipient has a job times the total unemployment rate in that state that month. So you could get this from Laos, times the share of the state's labor force that is associated with an occupation. So this is a bit of a detail, but you could get this using both the unemployment numbers from the ETA data and combining that with employment statistics by occupation from the BLS OEWS, so Occupation, Employment, and Wage Statistics. Here, just to show you, though, that these more typical things, so looking at employment share or total unemployment, are actually not explaining all of unemployment risk. So I think a natural assumption is that employment share will be anti-correlated with unemployment risk. If employment is going up for an occupation, unemployment risk for that occupation should be going down. But actually, that's not always the case. For example, computer and math workers in Nebraska have employment share and unemployment risk that are pretty strongly correlated over time. Another example, management workers in New Hampshire have basically no relationship between their unemployment risk over time and their local employment share in the state of New Hampshire. Here in gray, you can see the distribution of Pearson correlations between employment share and unemployment risk over time for each state occupation pair in the data set. And you can see that these relationships span from being positively correlated to negatively correlated. They're all over the place. What about total unemployment rate? Now, if total unemployment rate predicts all of the variation in unemployment risk, this means that systemic factors are completely governing the unemployment risk experienced by each worker. And what we find is that this is not the case. So for example, life, physical, and social science workers in Wisconsin have a negatively correlated unemployment risk compared to the total unemployment rate in that state over time. Here in this blue distribution, you can see the distribution of Pearson correlations between total unemployment rate in a state and the unemployment risk for that state occupation pair over time. You can see that most of the time, these quantities are in fact positively correlated, but sometimes they're negatively correlated. So the unemployment risk is not totally explaining all of this. Another way to appreciate this difference is to actually look cross-sectionally. So here, for example, we have states' total unemployment rates in March 2020. So COVID is a factor here in green. And then in red on the right, for the same month, March 2020, we have the unemployment risk for healthcare and support workers. And you can see that these maps do not line up. So there's some more information in unemployment risk compared to what you get if you're just looking at total unemployment rates in states. If you want to explore this data for yourself, you can follow this link to see a live demo where you can play around with this data. It's especially interesting for comparing to trends during 2020 month to month. So what about our study here? So in this study, we're going to focus on this collection of studies that produce probabilities of computerization or AI exposure scores for each occupation in the US. Now, what you can see is that these studies really span the last decade, and we've done a lot of growth in this body of research over time. I like to break these studies up into basically 3 waves. The first wave being based mostly on theory. So ideas, for example, like routine bias or skill bias, technological change, where cognitive non-routine workers are assumed to be less exposed to AI than routine physical workers. Or maybe also using heuristics like workers who have bachelor degrees, we assume to be less automatable. In the second wave of studies here, We tried to be more empirical about what occupations require of workers. So what are the skill requirements? And among those skills, what do we think AI can do, usually based on survey techniques? A third wave of studies down here tries to be more empirical about what AI can actually do. So for example, in Michael Webb's study, he analyzed AI patents using natural language processing and compared those technology descriptions to descriptions of occupations to try to figure out which occupations have AI exposure and might be automated by new technologies moving forward. So you can see there's been some growth and sophistication as new data enables new analysis across each of these waves. Now, even though we've been doing this for a decade, each of these studies validates their scores in the same three ways. They compare their occupation exposure scores to educational requirements, changes in employment share, or changes in wages. And as I've shown you, these things don't necessarily correlate to at least unemployment risk and might not relate to job separation rates either. So if we've been working at this problem, trying to figure out which occupations are most exposed to AI for a decade, perhaps we've been converging on a good solution. So here what I've done is I've pulled individual scores from each of those studies, and I've given them some nicknames, so I know they're a little hard to recognize. But basically, they're in chronological order here, where older scores are at the top, newer scores are at the bottom, and similarly, older scores are on the left, newer scores are on the right. So these three scores come from Michael Webb's paper. First thing you'll notice here is we're just correlating these scores to each other in this matrix, and basically they're not strongly correlated with each other. It does not appear that as we move from older scores to newer scores, that there's sort of this convergence onto a single solution and scores start to be correlated with one another over time. Another way to see this, this lack of agreement is to here look at our scores again on the y-axis, and here look at over 900 different US occupations and their exposure scores as these thin vertical stripes. Now, I'm not going to label all these occupations, but I have grouped them into major occupation categories to give you a sense for which occupations fall in which category. And as you look from top to bottom on any of these individual strips or within either of these major categories, what you see is that it's pretty noisy, again, indicating that there's not a lot of agreement among these different efforts to estimate which occupations have the most exposure to AI. Well, now we have a new measure, this unemployment risk for each occupation and state, which gives us at least one thing we can about job disruption, quantifying job disruption that might relate to exposure to AI. So first, let's do the dumbest thing and just measure the Pearson correlation between these different AI exposure studies scores and unemployment risk. Now, what you can see is that individual scores don't estimate or don't predict a lot of variation in unemployment risk across occupations, month, and state. The most predictive set of scores comes from the Arntz et al. OECD study here, accounting for about 11% of the variation in unemployment risk. If you group these scores into those waves I pointed to before, you can see that there is some modest improvement from wave 1 to wave 2 to wave 3. But again, it's not accounting for a lot of the variation in unemployment risk. So what's going on here? The first possibility is that AI is not a factor in unemployment risk, and any honest effort to try to relate the two would result in a really low R-squared. A second possibility is that we saw that these efforts over the last decade don't appear to be converging to a single solution. And so maybe we're just not good at estimating which occupations have exposure to automation from AI. A third possibility is that these studies span the last decade, and they've focused on different technologies and different sectors over that period of time. So maybe individually, they don't explain a lot of variation in unemployment risk, but when taken together, they can actually explain a lot more of the variation in unemployment risk. So to test this idea, here we're using lasso regression. And here, first of all, in this first model, we're just throwing all of those AI exposure scores into a single lasso regression model and letting the lasso regression figure out which of these scores are predictive in the presence of other scores. And what we find is that a really large share of variation, 20% of the variation in unemployment risk across occupations, month, and state is explained by these AI exposure scores taken as an ensemble model. Now, of course, this wasn't very careful, this modeling effort. There are a lot of potential confounds. that we would like to control for. So to try to do that, we're going to introduce this model 2 as a baseline model. This baseline model controls for the percentage of workers of each occupation with at least a bachelor's degree. It controls for occupation skill requirement. It also controls for year, month, and state fixed effects, which will account for big temporal trends like the recovery from the Great Recession, regional variations, for example, access to natural resources or report, and monthly fixed effects will account for seasonality, for example. And that baseline model explains a ton of the variation in unemployment risk. It gets about 70% of the variation explained. However, when you throw back in our AI exposure scores on top of this baseline model, you get an impressive additional 12% of the variation explained in unemployment risk. And when you look at the lasso regression coefficients, what you see is it's not just one or two of these predictions that are doing the predictive work here. There are many coefficients that are pretty large and significant, indicating that it's actually the collection of these AI exposure scores that are doing the work in this predictive exercise. Now, it's not just unemployment risk, and also sort of the focus here, but the focus here and the hope is to actually get at that whole pipeline of job disruption that I mentioned before. And here I'll tell you some results using the best data that I've been able to find to study each of those parts. Also, that previous effort was really focused on the prediction, that R squared. And so really the better thing to do is to train a model on training data and use cross-validation to test it on validation data that was held out of training. So here we're doing that and measuring the variance explained in that held out training data, comparing the baseline models using these pale colors to when the AI exposure scores are added to the baseline model in these more solid colors. The different colors represent looking at unemployment risk with variation by year, month, state, and occupation. Here, look in orange, looking at the variation in total unemployment rate. In green, looking at the variation in total job separation rates by state, year, and month. And finally, looking at the variation in occupations skill change according to ONET over a 10-year period. In all of these cases, what you see is that the inclusion of these occupation exposure scores significantly improves the model's ability to predict the variation in these different types of job disruptions. In fact, here on the right, you can see the factor improvement in the overall prediction using these validation data sets. You can see that our ability to predict unemployment risk, total unemployment rates, job separation rates, all improve by, let's say, 17 to 20%. But the largest improvement is when we look at the change of within occupation skill demands here, where we're able to improve the predictions by over 50%. Another nice thing about this ensemble approach is it gives us a way to try to diagnose where different studies' scores are performing well or not performing well. So here, for example, the color tells you the occupation state pair's unemployment risk and how that how that unemployment risk relates to the ensemble model's prediction on the y-axis or the scores taken from one of these two studies, the Frey-Osborne study or the Michael-Webb study on the x-axis. And by looking at the bottom left to top right in each of these plots, you can see where these two models agree. And by looking at the off diagonal, you can see where the two models actually disagree and where the ensemble model is outperforming the single study on its own. Now, moving forward, what I'm hoping to do is get similar data on unemployment risk, at least by industry or occupation, for sub-state regions, for example, looking at counties. I think this gives us a really interesting tool for not just studying AI and job disruption from AI, but also looking at job disruption from other regional policies. So, for example, looking at the Inflation Reduction Act and how that might help or hinder fossil fuel workers as they try to find their next employment opportunity. Beyond this, I'm really interested in better understanding technology and changes to the demands for specific skills. I'm hoping to get unemployment risk data for counties and for cities. And I'm interested in connecting labor market outcomes from resumes to workers' education to figure out what types of foundations make workers adaptable to AI or to other labor disruptions.
So hello, everyone who is watching this, whoever is watching this room record right now. So actually, we presented our paper at the Wharton Business School's AI and Wharton conference, but due to some technical difficulties, we have to re-record it, so you're watching this Zoom record right now. My name is Nisa. I am a third-year PhD student in Public Policy and Management at the University of Southern California, and my co-author Yi here is also with me. He will also walk you through some of the methodology parts of our paper. So let me go ahead and start. Our paper is Complementarity, Vulnerability, and Replacement, Artificial Intelligence in the United States Federal Labor Market. So I know it already sounds a little bit different than the rest of the business school papers, which is because we are mostly looking at the governmental organizations rather than the private corporates. Well, the starting point of our research was this actually curiosity about like how the AI integration into public organizations was going to influence the roles and the required knowledge, skills, and abilities for the governmental workforce in the United States within the next 5 years. Why do we specifically focus on this though? The part that we are mostly interested in is the KSAs, which stands for knowledge, skills, and abilities, because we believe that the AI is going to impact the employees within these specific buckets of their job description. But our motivation also stems from the specific needs of the public sector, because as Allison also says, the public sector and private sector are similar all in unimportant aspects, but they actually differ in all important aspects. So the idea is that the public sector has different motivations, they have different responsibilities, they have different rules within their organizations, and actually it kind of differentiates them from the rest of the private sector. That's why we are specifically looking at the public sector labor market and how it is going to be shaped, because US is one of the leading countries in the AI development, and actually even every single governmental office is trying to employ this. They're trying to adopt some AI tools, but our curiosity is how it is going to impact this specific labor force. Our research setting actually starts at the federal level, but then we are step by step coming to the city level from the California states, the counties in Greater LA, then cities, again within the same region. We are mostly focused on the Southern California as of now because we are USC, we are a Southern California university, and this is our kind of the interest and where we have the connections with. But the idea is that hopefully we will try to actually expand the scope of this research in the near future. So let's talk about our methodology a little bit. We are actually using two different methods. It's kind of creating a synthetic data set through AI tools to understand the perspective of the machine, versus the second data set, it is a qualitative data set that we will collect through some interviews and surveys that we will conduct with the actual governmental employees working at these jobs. So I will actually leave it rest to Yi, and he will walk you through the first set of our data sets.
Thank you, Nisa. So hi, everyone. This is Yi, and I'm an incoming PhD student at USC Price. So the first set of data is a synthetic one that created by a knowledge-enhanced large language model. It goes through a two-phase process. So first, we ask the LLM to identify the knowledge, skill, ability, and duty from a job description of the government occupation. And then the extracted KSA will be used to assess the 5-year impact of AI on the occupation. And then finally, give an aggregated index score for the occupation based on the impact level of each KSA. Next one, please. So to achieve this, we use a LangChain framework to create a knowledge-enhanced LLM that integrates RAG. So the goal for doing that is to let the vanilla version of LLM become an expert in job description analysis by providing it with some specialized knowledge. So we first build a knowledge base that contains a number of government issue documents about KSA and occupations, and then fit this to the LLM. Then we ask the LLM to first retrieve information from those knowledge base, and then before generating the KSAs. By doing so, the LLM has a better understanding of the whole context, so the generated result of LLM becomes more consistent and deterministic instead of just stochastic. Also, we apply some data pre-processing steps on the job description, like name entity recognition, to further help the model avoid a misunderstanding, such as polysemy, in the result of generating the LLM. Also, something I like to point it out is compared to the private sector, public sector jobs have well-structured and organized job description for every occupation, and all of them follow the same rules in a certain government. So in this specific task, the LLM can provide higher quality result in terms of accuracy and consistency. Next one, please. So the phase 2 basically follow the same process of phase 1. We first give the LLM some reference materials about AI's impact on the labor market, and then ask it to provide AI's impact level for every single KSA across 5 levels. Ask the model to assess if this required knowledge or skill of this occupation is vulnerable to AI or not. And then finally, we will have an aggregated AI impact index for this occupation. And these are our ongoing works to improve the quality of results, include reference materials from more different knowledge sources, such as macroecon reports, recent government policy about AI, etc. And also keep optimizing the prompt and also pilot the task on different LLMs. Next one, please. So I will show you guys an example of how it works. So this is a job description for Workforce Development Series. It is a category of federal government jobs focused on designing, implementing, and managing programs aimed at improving the skill and employability of the workforce. We use different colors here to represent potential knowledge, skill, and ability. We just use common sense to color these words that may be required KSA for this occupation. Blue for knowledge, red for skill, and black for ability. Let's see how this works. So as you can see, this is the result of phase 1 returned by the LLM. Most keywords have been successfully extracted by the model. We also asked the LLM to give an explanation of why you think this is a required KSA. The purpose for doing that is for future validation by human experts, which is our next step, do a qualitative interview with government employees. Next one. So this is the example of the result of phase 2. As I mentioned before, we fit the result of phase 1 back into the model, and it's going to return a level of AI impacts for every single KSA. And then by aggregating all of the KSA impact scores, we get an average index for this occupation. You can see for this one is 2.83, refers to moderate. Something I like to say is this is just a very preliminary example of the result. We're not satisfied with just simply averaging the score of each KSA. Instead, we have many future plans of it. What we're planning to do is to add weight on each KSA when calculating the impact index of the occupation. And the weight will be based on the result of our qualitative interview with government employees. Next, I'll pass back to Nisa to introduce the qualitative analysis.
Yes, thank you so much. So as you guys have seen, actually, like just walked us through the synthetic data creation actually through the machine. So that's the machine side of the data set that we are going to use for our paper. But then we also want to have like the human perspective, how the people who are actually doing these jobs perceive the impact of AI. So what's going to happen? In this part, we will actually conduct some individual interviews and qualitative surveys with the people who are working at certain governmental jobs. But they will not be some actually random people. Rather, we will also focus on like the occupations that will be impacted the most, the moderates, and finally the lowest. So the idea is that actually like see also like different levels of impact and how the human perspective differ or show similarity to the machine's perspective. Because we understand that like AI keeps evaluating itself, it keeps developing, and every single time we actually ask the same question, it's going to give us slightly different answers. So our research will be actually a snapshot of the current version of the AI. But the overarching goal here is actually also testing the predictive abilities of the AI tools. Because within the 5 years, we will see like how much of this like AI perspective versus human perspective holds significance and actually fulfills itself or not. So what do we anticipate? I mean, the goal here is actually like having a detailed impact scores for the governmental roles and actually provide the governmental agencies with some strategic insights. Because again, another difference between the public and private sector, the public sector most of the time lacks some of the abilities, actually technological abilities, which private sector most of the time have more, and they do not have a clear understanding of how the technologies are going to impact their organization. They most of the time have collaborations, they have vendors that they work together, so they can actually keep up with the rapidly developing and evolving technologies. So the idea of this research is also actually providing this public sector who lacks such access to this type of information, to these strategies, how to shape their policies, how to shape their investments in the workforce development, or how to ensure that their workforce remains also robust and capable, no matter how the technology actually impacts the organization. Going back to challenges, it's a little bit of cliche, but we know that in quotation marks, there are always black boxes of AI tools. We do not exactly know what are the training materials that they use for these immensely large language models, or how they were trained, or how the algorithms are exactly working. But this is not just a challenge for us, it's a challenge for anyone and everyone who actually works with AI. We still would like to also acknowledge that. And second thing, as I said it previously before, it will be a snapshot of the current development of AI. Within 5 years, it might actually result in some differences in the interpretations of the workforce development and workforce impact. So the idea is that hopefully this research will be an ongoing research, and we will not just do it now and leave it be. But the idea is that maybe within a 5 year, again, we will actually repeat the same thing with the same method, same approach, and actually see if there are any changes. And lastly, we would like to acknowledge our US Clear and Data First Science team, who are all USC data science master students who actually helped us and still helping us to create and develop this large language model. And our professor, William Resch, also has a lot of impact of our research. So yeah, with that in mind, I would like to end our conversation here. I know there is no one here watching us at the moment live, but if you have any questions, if you have any comments, please feel free to reach out to us. I believe our contact information will be a part of this recording. So we are always more than welcome to your questions. Thank you so much.
Yeah, and please feel free to find more details about this project on the uscclear.com.